Welcome to The Explainer. Today we're getting into some pretty technical papers that are proposing a radical shift in how we think about AI's safety. We're moving away from asking if we can trust an AI to building systems where, honestly, trust just isn't part of the equation, because safety is guaranteed by math and engineering.
Right. This question. It's been at the heart of the AI alignment debate forever. But what if it's the wrong question to be asking? The research we're digging into today suggests a totally different path. Forget about trust. Instead, let's engineer systems that guarantee safety through verifiable, machine-enforced control.
So, to really get this, we're going to build the whole idea from the ground up, kind of like a tech stack. We'll start with the pure math, then layer on the engineering blueprint, turn the rules into code, look at the big picture risks, and finally see how it all clicks together into a complete system.
Okay, let's dive in. Our journey here starts at the most fundamental level possible. The whole idea is to reframe what AI alignment even means, turning it from a fuzzy, philosophical problem into a crisp, mathematical one.
See, this new approach doesn't really care about what an AI is thinking or what its goals are. It only cares about what we can actually see, its actions. This is formalized as its behavior law, which is represented by that Greek letter mu. You can think of it as a complete map of every single thing the AI could possibly do and how likely each of those things is.
And this is where it gets really elegant. Alignment becomes a simple, clear mathematical statement. Mu must be a member of S. All that means is the AI's total behavior, that's mu, has to stay inside a predefined boundary of what we consider safe and acceptable behavior, that's S. We're not trying to teach it values. We are literally building a fence around its actions. Okay, so a mathematical rule is great in theory, but how do you actually enforce it in a real-world system? Well, that's where we jump from the theory to the engineering, with a concrete blueprint for control. The answer is something called the Verifiable Governance Architecture, or VGA. And at its heart is a component called the Watchdog. Now, this isn't some passive monitor. It's an active gatekeeper. It intercepts every single action an AI agent tries to take, whether that's sending an email or executing a stock trade. It stops the action and then checks it against the rules. And this is the absolute core principle. The system runs on a powerful security idea called fail-close, or you might know it as default deny. Unlike a system that lets things through unless they're proven to be dangerous, the watchdog denies everything by default. The only way an action gets through is if it can be mathematically proven to be safe and compliant. If there's any doubt, any ambiguity, the answer is just no. And here's where the architecture gets really smart about managing risk. It's not one size fits all. The system gives AIs different seniority levels. A junior agent, for example, is stuck in a sandbox with read-only tools. A professional agent can suggest big moves, but has no power to actually execute them. And for a senior professional agent to do anything irreversible, it needs multiple other parties to co-sign. This whole idea comes from cybersecurity. It's designed to make sure the system stays safe even if one part of it goes rogue. No single point of failure.
So that brings us to the rules themselves. In this framework, governance isn't some dusty policy document that sits on a shelf. It is living, breathing, executable code. It's a set of policies that the watchdog uses to make its decisions in microseconds.
And to make sure there's total accountability, every single decision the watchdog makes, allow or deny, creates something called an evidence packet. That packet then gets locked into a tamper-proof hash-linked log. You can think of it as a blockchain for AI actions. It creates this perfect, unchangeable audit trail, so you always have cryptographic proof of what happened.
Now you might be thinking, doesn't checking every rule for every tiny action slow things down? And you'd be right. That's why the system is smart about it. It uses a risk-based approach called minimal viable verification, or MVV core. It picks out the most critical must-have laws, like preventing harm, logging everything, and that default deny rule, and it enforces those relentlessly all the time. These are the always-on rules that guarantee the system's basic safety.
So far, we've been talking about controlling a single AI. But in the real world, companies are going to deploy fleets of these things. And that opens up a totally new and frankly much scarier kind of risk. Not just one agent failing, but the entire system collapsing because of AI monoculture.
So just imagine a big bank. They deploy, let's say, 100 agents, we'll call that N, to manage their portfolios. And for efficiency's sake, all 100 are running on the exact same foundation model from the same company. This is a super common setup.
Well, here's the terrifying part. If that one model has a single hidden flaw, the risk of a correlated failure, where all 100 agents make the same catastrophic mistake at the exact same time, it doesn't go up by a factor of 100. The math shows it scales exponentially, as n squared. That's a 10,000-fold increase in risk. One tiny bug could trigger an instant systemic collapse.
So how do you fight that? Well, the framework introduces a measurable, quantifiable metric called the heterogeneous score. This isn't just a vague suggestion to use different models. It's a hard, auditable score that's calculated by comparing how different the models are on the inside and in their outputs. If that score gets too low, it means your models are too similar, and the system automatically blocks high-impact actions until you increase diversity.
And it goes even broader than that. The system acts like its own internal regulator, with a feature that's basically a contagion thermostat. It calculates this value, the spectral radius, which measures how tightly interconnected and interdependent all the agents are. As that number gets closer to a critical threshold, alarm bells go off. It's warning you that the system is approaching a phase transition. You know, like when water is just about to flash freeze into ice. It's the point where one small local error could cascade into a total systemic crisis.
Okay, let's pull back and put all of these technical layers together. Let's look at the final picture, the complete end-to-end stack for verifiable AI governance.
You can really see how we've built this thing up layer by layer. We started with new axioms, defining alignment by what an AI does. That led to a mathematical theory of containment. We then operationalized it with the Watchdog architecture, which in turn generates the evidence we need for certification. And the whole thing is wrapped in a top-level governance layer that manages those huge systemic risks, like monoculture. It's a full pipeline, from first principles all the way to enforceable control.
And this, right here, is the single most important idea to take away from all of this. System safety is decoupled from the AI model itself. Think about that for a second. The underlying AI can be a black box, it could be biased, it could even be adversarial, it doesn't matter. The deployed system is safe by construction because this external wrapper acts like a filter, forcing its behavior to stay within that safe boundary. Safety is no longer something you hope for. It becomes an enforced architectural property you build from the start.
This shift from trusting models to proving system safety, it creates an entirely new paradigm for AI. But it also raises a pretty profound question for all of us. If an AI system's safety can be mathematically proven, and its actions are logged in a way that can never be changed, who's ultimately accountable when something still goes wrong? This new architecture of control might just reshape our entire understanding of responsibility in the age of AI.